Good evening, dear colleagues from all around the world. My name is Luis de Bellis, and it's a great pleasure for me to be here with all of you today to present a major advancement in the MetiSmile facial scanner from Shining 3D. This breakthrough has undoubtedly revolutionized the way we work with our patients. We are not being just able to make a facial scan to improve communication with our patients and colleagues, but we can also use it as a high-level diagnostic tool, and it now allows us to record mandibular kinematics. This positions it on the same level as other devices currently on the market, which have already proven to be great allies in the visualization and planning of our treatments. We are living in a time where being a dentist is truly inspiring, and with the rapid evolution of technology and the rise of the digital patient, the study of facial morphology has reached a new level. Traditional 2D photographs and mathematical tools are no longer sufficient to capture the complexity of the human face. Three-dimensional facial scanning enables fast, non-invasive, and highly realistic acquisitions of facial structures. This is critical in multiple dental disciplines like prosto, ortho, and craniofacial surgery, and not to be less important, digital smile design. The key advancement is that facial scans can now be merged with intraoral scans and combine computed tomography to create a virtual patient. For example, in this paper done by Dr. Conejo, the main goal is to show how we can combine facial scans, intraoral scans, and CBCT data to create what the authors call a digital clone, that is a virtual version of our patient that brings together aesthetics, function, and anatomy. This digital model allows us to plan treatments more precisely, predict outcomes more accurately, and truly personalize care across multiple dental disciplines. But how is that all this machinery interrelates, and how can we actually achieve predictable, reproducible, and practical results? We all know that the basic starting point today in digital dentistry are intraoral scanners. These devices have evolved to such an extent, and the accuracy and speed with which we can digitize the intraoral anatomy of our patients make them extremely reliable and comfortable. However, they only provide the digitalization of both arches, like we can see here in this slide. We can clearly see that we have exported the intraoral anatomy digitalization from our intraoral scanner software, but it lacks basic information that is essential when we consider a complex oral rehabilitation, which will likely involve an increase in vertical dimension. Anyone attempting to carry out complex procedures with only this information will undoubtedly face more than one clinical complication, like the one we can see in the next slide. Here, an increase in vertical dimension and tooth setup was performed based solely on intraoral scans, which resulted in premature contacts at the molar level. But the question is, why does this happen if hypothetically intraoral scanners are greater on their own? But as we all know, he who does not know history is condemned to repeat it. When we practice analog dentistry, we would never consider rehabilitating fully edentulous arches with just a simple articulator mounting like the one shown in this image. Not only does this go against basic principles, but there wasn't even the precaution of leaving the occlusal plane reasonably well leveled. And for example, the same thing happens today with digital dentistry, where we obtain intraoral scans and we relate we relate them to different devices. For example, the one shown in the image on the right, which is a hinge. This hinge doesn't meet any anatomical parameters, and it is positioned exactly at the level of the occlusal plane. This is completely unrealistic, as no human being within normal parameters present such morphology. Therefore, the arc of opening and closing described by this device will differ from the patient's real movement, resulting in what we saw earlier, premature contacts at the molar level. In the image on the left, we see pins that simply serve to relate the modules, but they do not fulfill any functional purpose either. So this is why we cannot forget about history, its evolution, and the impact this evolution has had on our daily clinical practice, an evolution that has benefited us for many decades. Since Guy Roth introduced the first device for mounting modules, followed by Snow with the creation of the facewell, and later Bissler's group in 2002, which introduced the concept of virtual articulator, we have since experienced a rapid race to develop equipment capable of accurately reproducing mandibular kinematics in the virtual environment. Virtual articulators can be classified into two groups: those that are mathematically simulated, which are analogous to semi-adjustable analog articulators, and fully adjustable articulators. Virtual articulators, for the mathematically simulated classification, have a main clinical indication that involves cases in which reproducing the relationship between the arches is sufficient to plan the occlusal morphology of the prosthesis. The main disadvantage is that it is not feasible to obtain individualized movements from the patient. Then we have fully adjustable articulators, and the main indication involves complex cases in which the morphology of the occlusal plane must be evaluated during mandibular movements to avoid interference in excursions. Today, thanks to various functions available in softwares, such as the Aoral 3 or Aoral Elite scanner software, which allow us to record mandibular kinematics, as we can see in the video, they still lack crucial information, which is vital when considering an increase in vertical dimension. These functions only allow us to visualize mandibular trajectories, but they do not enable us to carry out more complex treatments due to the absence of essential data that we can appreciate in the next slide. In this slide, what we can observe is that in the same case, I have positioned the condyles of the virtual articulator in different locations. In the image on the left, we can see the virtual articulator's condyle positioned in relation to the patient's actual condyle. And we notice that the opening and closing trajectory is completely different from the trajectory seen in the image on the right, where the virtual articulator condyle has been positioned far from the patient's condyle. What I want to illustrate with this is that when we lack critical information, such as the relationship between the lower incisal point and the patient's condyle, we end up with trajectories that differ from those of the patient. This will lead to undesired occlusal interferences when attempting to modify the patient's vertical dimension. So the problem I want to highlight is that even though we have virtual articulators, there is still a gap that needs to be filled in order to achieve clinically satisfactory results and make our treatments more predictable. This gap is simply filled by images. Since Dr. Kochman introduced the concept of digital smile design, we have gradually seen how this gap has been filled thanks to the evolution of technology. In the first generation of DSD, all we could do was sketch teeth over photographs. As technology evolved, we moved from 2D images to the 3D environment. By the fourth generation of DSD, we have been able to integrate 3D models with facial scans, which has allowed DSD to become more than just a communication tool between the patient and the dental technician. It has now become a more precise diagnostic tool that over time has evolved hand in hand with the technology made available to us today by companies like, for example, Shining 3D Dental. And Shining 3D Dental did this possible with the MetiSmile. Many of you might be asking why MetiSmile is so different to other facial scanners in the market, and the answer is pretty simple. It has been designed by clinicians for clinicians. To start with and show why I like facial scanners, I want to show this study that explores the clinical applicability of 3D facial scanning in comparison to traditional 2D clinical photography for identifying soft tissues landmark. While 2D photography has been widely used for orthodontic and surgical diagnostics, 3D scanning offers depth perception and detailed spatial data, with increasing applications in orthodontics, prosthodontics, implantology, and facial surgery. From my point of view, the MetiSmile is today's modern Facebook. It not only allows me to scan the face like any other scanner, but it also enables facial scanning with certain considerations that are vitally important for those who wish to use it as a diagnostic tool. The first and most basic thing we need to understand about this scanner is that it does not operate using structured light or laser technology like other facial scanners. Instead, it uses infrared technology similar to the front-facing cameras of iPhones. This allows us to scan the patient's face without them having to close their eyes. For the field of prosto, this is critically important because it enables us to capture a fundamental and essential reference, the bipupillary axis. The other features of this scanner will be discussed throughout the rest of the presentation. In this slide, we can see three different situations, three completely different patients whose faces are being scanned. We can observe that the patients do not have their eyelids closed, nor are they straining to keep their eyes open. This is thanks to the infrared technology of the MetiSmile, which is truly user-friendly and, on top of that, scans very quickly with optimal results. One of the advantages of the MetiSmile also, thanks to its hardware and software, is its ability to provide excellent depth of field. In contrast, as we can see in this slide, a facial scan performed using a mobile application resulted in almost no depth of field in the perioral region. This will lead to the intraoral scans being aligned in a more anterior position than the patient's actual anatomical position. As a consequence of the anterior shift, there will be a deviation in the distance between the condyle and the lower incisal point, resulting in a significant discrepancy between the virtual environment and reality. Therefore, when we bring our virtual designs into the real world, they will not meet our expectations. Here we can see what we were speaking about, the alignment. This is a publication that it's pretty old, but it shows what we are speaking about. On the other hand, thanks to MetiSmile's depth of field and software development, the MetiSmile allows us to obtain scans with excellent depth of field, sometimes even capturing up to the area of the second premolar and first molar. This makes possible to perform an easy and precise alignment of our intraoral scans with the facial scan directly within the MetiSmile software without the need for additional devices that could complicate our workflow. And as we can see here, I'm using the color map verification within the same software to check the accuracy of the alignment between the intraoral and facial scans. This allows us to export the aligned data directly to the design software of our choice without the need to perform the alignment in third-party software. And in this simple way, thanks to technological advancements, we can continue along our path of virtual planning and approach that has already been validated by various studies. In this publication, we can see how by using facial scan and an intraoral scan, we're able to more accurately orient the condyles in our virtual articulator, which result in greater precision when carrying out our virtual planning and ultimately in the materialization of our design. Another point I'd like to highlight and differentiate from what we've seen in this publication compared to the previous slides is that thanks to the technology of the MediSmile, we can do the intraoral scans and facial scan alignment without additional devices like the one shown here. The basic digital workflow of the MediSmile and the possibilities offered by its software are truly powerful for everyday clinical use. Not only can we perform facial scans, but we can also carry out facial and dental analysis using artificial intelligence. This allows us to quickly obtain a diagnostic orientation, which must then be validated by the treating doctor. For example, in this slide, we can see some of the measurements performed by the software. Thanks to artificial intelligence, these measurements can quickly guide us in defining certain parameters for our treatment. Another crucial point is that everything we see and do within the software is saved, allowing us to track and compare the changes the patient undergoes throughout the course of the treatment. In this slide, we can also see how the software can provide a demonstrative simulation of the potential progress of an orthodontic treatment. This animation is for demonstration purposes only and should by no means be considered a treatment plan. It is simply intended to show the patient a possible outcome of how things might look. But how can we get the most out of it? Obviously, always speaking about MediSmile. And the answer to the question from the previous slide came in 2025 by taking advantage of the infrared technology of the Medis Smile, reflective stickers were developed which can be attached either to the device shown on the screen or directly onto the patient's teeth. Thanks to these reflective stickers and the outstanding work by the engineers at Shining 3D Dental, we now have a facial scanner that not only serves the purposes we previously discussed, but also allows us to track the mandibular trajectories of our patients, just like other existing devices on the market, such as the Mojo. The major difference between using the facial scanner for this function and performing mandibular tracking with the Aoral 3 or Aoral Elite software is that the facial scanner enables us to record a wider range of movements rather than just a few millimeters, as in the case with the intraoral scanners. This article provides a comprehensive review of the current digital technologies used in occlusal analysis with a focus on intraoral scanners, jaw motion analyzers, and digital articulators. It highlights how intraoral scanners have advanced from simple surface data acquisition tools to instruments capable of recording static occlusal contacts, although their limitations in capturing dynamic occlusions remain. The authors evaluate different jaw motion analyzer systems that record mandibular movements using sensors and tracking devices, emphasizing their importance for dynamic occlusal assessment and individualized patient care. Digital articulators, both mechanical replicas and virtual platforms, are discussed in the context of simulating occlusal function and facilitating digital workflows. Ultimately, the article underscores the need for integration of these tools to improve diagnostic accuracy, treatment planning, and patient outcomes in prosthodontics and digital dentistry. But the question, how does this really work? The first thing we need to know are the changes in the user interface. Now we can see that in addition to performing facial scanning for registration and facial analysis, two new functions have been added: mandibular movement trajectory tracking and optimal jaw relation. Both functions can be used complementarily depending on the requirements of each clinician. We will start with mandibular movement trajectory tracking. Many times we tend to get confused and we think that both modules from this software work in the same way, but as I said, they are complementary, and we should understand this, and I hope that you can understand it with this presentation. The first example that I'm going to show is mandibular movement trajectory tracking. As with everything we do in the 3D environment, we must first create a proper work order so that the software can guide us through an organized protocol that results in something clinically useful. In this sequence of images, starting from the top left of the screen, we can see that the first thing I do when beginning a work order is upload the patient's intraoral scans. Then, as shown in the top right image, I select the mandibular movement trajectory tracking option. Once the option is selected, I'm given the ability to upload the patient's DICOM files, which, if available obviously, will be extremely useful for visualizing the condylar trajectories within the glenoid fossa. Finally, to begin the process, we press the scan button and the software will ask whether we will be scanning with the reflective stickers placed directly on the teeth or using the tracking device. In this slide, we can see the software is asking us how many stickers we will be using on the upper and lower arches. If we are using the tracking device, this option will not appear as the tracking device always operates with 4 stickers. Something we must keep in mind when using the stickers is that they should not be perfectly aligned or placed too close together, as the scanner may have difficulties while detecting them. They must be positioned with some degree of variation between them, and we must also ensure that the stickers are not covered by the lips during opening and closing movements. If we determine that these conditions cannot be met, it is better to consider using the tracking device instead. In this video, we can observe how the scanner recognizes the patient's face and the number of stickers placed on the tooth surfaces. The scanner will not begin operating until it detects the exact number of stickers specified in the work order. Once it recognizes the number of stickers indicated in the order, it will prompt the patient to slightly open his or her mouth. This allows the scanner to complete the sticker recognition process and enables us to perform a basic facial scan, which will later be used to align the intraoral scans with the facial scan. Once we complete the initial scan, the artificial intelligence will align the intraoral scan with the facial scan, and we must verify the accuracy of this alignment using the color map. If the alignment is not correct, please, you have to manually adjust it by selecting matching points between the facial and intraoral scans. It is important to verify this at this stage because if we don't, we may end up with an incorrect relationship between the maxilla and the mandible during the mandibular tracking process. Here in this video, you can see how the workflow prompts the patient to perform different movements. Typically, we ask for opening and closing, followed by protrusion, and finally lateral movements. As shown in the video, when the patient performs movements that are too fast or exaggerated in trajectory, the scanner loses tracking because it cannot correctly identify the stickers on the tooth surfaces. Therefore, it is important to train the patient beforehand to ensure a satisfactory result. It doesn't take too much time to do all this. In around 5 minutes, you have everything set up, but you have to follow the indications that I've done previously to all of you. Next, we will perform a facial scan at rest so that it can be aligned to the previous scans. This is a must. And once we have completed the scans, the software will prompt us to mark certain strategic points, such as the outer poles of the mandibular condyles and the lower incisal point. This will allow the software to perform mandibular kinematic tracking, enabling us to evaluate the different trajectories across the various spatial planes. In the video shown in this slide, we can see how, thanks to the points I previously mentioned that need to be marked, the software is capable of displaying the mandibular trajectories in different spatial planes according to our needs. In this video, we can also observe how we can interact with the timeline to view and evaluate the trajectories more slowly and carefully. This analysis can also be performed with different scans layers. What I mean with this is that we can superimpose the intraoral scan onto the CBCT to get a better view of the teeth trajectories and evaluate the degree of mesh overlap. Additionally, we can make sagittal slices of areas of interest to view them in 2D and take measurements of specific regions. Here, as you can see, I'm going forward and backwards in the timeline. I'm just playing to show what it can be done. And there you have the 2D sagittal cut that also can be placed in different parts of the 3D space so that you can check into the sagittal cut of the condyle and glenoid fossa or whatever you want. In this video, what I want to show is that the trajectory in the CBCT is exactly the same as what we see in the scanner's camera, which means the information transfer within the software is well executed. From my point of view, this can perfectly replace what we used to do a few years ago, marking points on the patient's face and recording videos to analyze different trajectories. Today, thanks to the technology of MetiSmile, we can not only evaluate trajectories on a superficial level, but also assess them at the bony level. Now I'm gonna be running over the optimal jaw relationship because I generally use what I've shown in these previous slides just for diagnostic purposes. You can also think about exporting all these movements onto Exocad, for example, and configure your articulator, your virtual articulator with all these trajectories so that you can get a better teeth setup and do whatever you want. But I really like this function that I'm going to be showing now, that it's the optimal jaw relationship. And let's jump into it. For the optimal jaw relation function, the file upload sequence in the work order is currently similar with what we've seen. The only difference is that it doesn't allow us to add DICOM files to visualize the condyle position in real time. I believe that this is gonna change in a few months for end users, but now we don't have this it's not possible for us. After uploading the files and pressing the scan button, the software will also ask whether we want to perform the kinematic registration using stickers placed on the tooth surface or the tracking device. It's exactly the same. The decision to use one method or the other is the same as we discussed in the previous cases. You have to check and see if the lips are going to be covering the stickers. Just like in the mandibular movement trajectory tracking module, in this video we can observe how the software must detect the number of stickers previously indicated. It then prompts us to perform a facial scan using the lip retractor so that we can align the intraoral scan with the facial scan. The main difference in this module is that, unlike what we saw earlier, here we must ask the patient to open and close their mouth at least 30 times so that the software can register the mouth opening and closing pattern. Obviously, I'm speeding up the video because if not, it's gonna take too much time. Once the software processes all the collected data, we will be able to visualize the mandibular opening and closing trajectory and perform increases in vertical dimension based on the patient's own opening and closing pattern. In the video, we can observe an increase in vertical dimension being performed. This increase is being done to assess how useful this tool can be in a clinical setting. For example, in this image, we can see the export of the upper and lower models. The lower model was exported in maximum intercuspation, and in green we can observe the mandibular model exported in the opened position based on the patient's own opening and closing pattern, as recorded by the Medis Smile that was shown in the previous slide. What I want to demonstrate with this is that by having the patient's opening and closing pattern information, we can fabricate an intraocclusal splint with greater accuracy, unlike what we would achieve if we only had the intermaxillary relationship without the facial and condylar position data of the patient, which we have discussed in one of the earlier slides. In these images, we can see the front and lateral views of the intraocclusal splint fabricated thanks to the export of the upper and lower model, which was repositioned based on the mandibular opening and closing pattern generated with the Medis Smile. In this image, in this slide, we can see the intraocclusal splint fabricated thanks to the export of the upper and lower model, which was repositioned using a jig, the Lucia jig that we all know from analog dentistry. And here is the comparison between something done by AI and something done by traditional dentistry. And to finish with, in this image, you can see the intraocclusal splint, which was designed in the way it is commonly done in digital dentistry for most cases. In this case, the record was taken in maximum intercuspation, and then a virtual mounting of the models was performed in the design software of choice. In my case, it was Blender for Dental. The increase in intraocclusal space was done arbitrarily using standard parameters in the configuration of the virtual articulator's condyles. After configuring the articulator, the splint was designed, and this one, along with the two shown in the previous slides, was printed in order to be tested in the patient's mouth. Here we have the three devices that have been printed in with Nextend Orthoflex resin and in my Acufab Cell 3D printer. After washing and post-processing them, I didn't polish because I just wanted to try the devices. And as we can see in the slide from left to right, we can see the splints created using the models extracted from Medis Smile software. In the splint, we can observe that all teeth are in contact with the splint. In the middle image, we can see the splint designed using an occlusal record that has been taken with a jig and only the intraoral scanner. The result is the same as the one obtained using MetiSmile registration. The image on the right side shows the splint designed using the intermaxillary record in maximum intercuspation and an arbitrary increase in intraocclusal space based on the default parameters of the virtual articulator. In this case, we can observe premature contacts in the molar region. This confirms the theory presented a few slides earlier regarding the opening and closing trajectory based on the location of the mandibular axis of rotation, which is applicable and should be considered in rehabilitation of complex cases. In these images, let me put this to work. Now, yes, in these images and videos, we can observe the same situation presented in the previous slides, but in a different patient. What I did is that I took a intraoral scan in maximum anticipation, that is the image in the right. Then what I did with that is that I asked the AI in Shining software to create a splint. In the middle picture and middle video, we can see the same intraoral scan with a jig to correlate the mandible and maxillary, and I created the splint in Blender, obviously. And in the right video, you can see that I'm using the optimal jaw relation to capture the opening and closing pattern of this patient, and then I exported this to design the splint. The result was this, and it's exactly the same we have previously discussed. With only the iOS information, the result is faulty. With the iOS plus jig, it's nice. And with the Medis Smile, we have a nice result. So if we don't have the Medis Smile with all these modules, we should think of getting an interrelation between maxilla and mandible, at least with a jig or something that can correlate in a better way and that enables us to export our intraoral scans in a better way than setting up our virtual articulator with arbitrary measurements. Another application for which optimal jaw relation works very, very well is the case of fully edentulous patients who need to be rehabilitated with removable prostheses. In this case, two wax rims were constructed in order to establish basic prosthetic parameters, just as we could do in analog dentistry. After constructing the wax rims, and thanks to the Edentulous workflow of the AORAL software, the wax rims were digitized and then aligned with the facial anatomy in the MetiSmile scanner software. This allowed us to integrate the intraoral anatomy with the patient's face. Then, as we have already discussed, the optimal jaw relation module was chosen to register the opening and closing kinematics of this patient. As we can see, in this case, the mandibular tracking device was used since placing the stickers on the wax rims was too complex. They were easily dislodged with the lip retractor. In the video, we can observe once again what we've been previously mentioned, performing at least 30 opening and closing cycles so that the software can gather the minimum amount of that data required to develop an optimal result. After exporting all these records captured with the Medis Smile, the file was imported into the chosen design software. In this image, we can see one prosthetic base in translucent yellow and another in pink, which show a difference of nearly 4 millimeters in the anterior-posterior direction. This difference is due to the fact that the yellow base was created from the intermaxillary record taken by the clinician in charge of the patient, while the pink base corresponds to the record obtained using the MetiSmile and the optimal jaw relation module. For this test, we printed the prostheses with the MetiSmile file. After printing the prostheses and before polishing them, they were post-processed to allow for intraoral try-in. This was done to verify the occlusion and ensure that the dental midline was aligned with the facial midline, which had been virtually confirmed through the facial scan. The facial scan also helps us orient the occlusal plane. In these images, we can see the prosthesis fully polished and finished. And in the video, the patient is asked to open and close his mouth in order to verify whether a stable occlusion was really achieved. And the result was, to be honest, astonishing. I didn't think that the result was going to be so nice. But as I didn't believe what I was verifying in the dental chair, we asked the patient to undergo a wide field CBCT scan with the prosthesis in place and in occlusion in order to verify whether the mandibular condyles were positioned within the glenoid fossae. We confirmed that the condyles were indeed within the glenoid fossae, allowing us to conclude that the system provided by MetiSmile is reliable for future cases, even when an initial CBCT is not available, as was the case here. The possibilities with the MetiSmile and the mandibular tracking devices are practically endless. As we can see in this case, the mandibular tracking device can not only be attached to tooth surfaces, but we can also have tracking devices that can be screwed onto the platforms of the multi-units present in the patient's mouth. You can almost feel all the cases that you can imagine. You have to combine these devices. You have a lot of possibilities, and obviously you have to train yourself in the workflows, because there are many ways to do the same. And to finish with, I would like to name this study that introduces a four-dimensional virtual patient that combines intraoral scans, facial scans, CBCT data, and geomotion tracking to capture both static and dynamic aspects of the patient oral anatomy. Using AI and CAD software, the authors created an efficient workflow for automatic alignment and integration of these datasets. This study concludes and highlights the potential of this four-dimensional virtual patient model to improve diagnostic accuracy, occlusal analysis, and communication in clinical dentistry, despite current limitations, obviously, like cost and technical complexity. The approach marks a key advancement in dynamic, personalized digital treatment planning. And to finish, I can conclude that digital jaw tracking is a key evolution in functional and prosthetic dentistry, valuable in temporomandibular disorders or complex occlusal cases. It's also valuable in Edentulous patients in neuroocclusally guided rehabilitation. Obviously, we need more clinical research on this field and in digital dentistry. We need more, because I believe that we need more protocols, personalized protocols for each case. And standardized protocols are also needed, as I was telling. And like the Johnny Walker slogan says, keep walking, please. And knowledge evolves extremely quickly, and surely everything we've seen today might be obsolete tomorrow. Thank you very much for your attention. And now we will be waiting for your questions and doubts, if there are any doubts. Thank you very much.